Oh, I hate that woman. Right. Okay, so we're going on. So now we're going to, where am I? Okay. So this is the bit about measuring and calculating enthalpies. And it's a very popular, practical to do. They're very simple to do. And with a spirit burner, I mean, if you've got a Bunsen burner, you can use that, but it's difficult to measure the amount of gas. But if you've got different types of alcohol, methanol, ethanol, you can put them in different spirit burners and see the effect on the same volume of water. You know this, and measure the temperature. And there are only a few things which people have to do. This is a proper KCSE examination question. And I'm just going to show you the bits and pieces which I think are important in doing this sort of question. There are marks, obviously, for just plotting the graph, for finding the maximum temperature, for finding the temperature change, then the moles and the molar capacity, heat capacity. Sorry, the molar enthalpy. And I've just done it here, and I'll just show you the things which I think are important. I used I used a very simple Excel spreadsheet to just plot the graph. So the graph is a bit rubbish, but I didn't have time to do it otherwise. Excuse me. But there's something which the students need to know, and you may remember on the endothermic one that we saw the woman doing the experiment on, that that would obviously go down. And what is happening is that we have added the sodium hydroxide at time 0. And what would be ideal would be if all of the heat was given out straight away and the temperature line went straight up here. And it would go higher than 29 because of the cooling effect of the room. So what we need to do is to extrapolate back from the numbers after what seems to be the highest temperature. And this is a skill that lots of students forget to do. And it's really important that they don't just go, oh, it's gone up to 29. So they have to extrapolate back. Now, this is only one extrapolation line. I decided not to take it onto the 26 and the 25 and so on, but I decided on this. And then the temperature, the true temperature rise is from zero time vertically up to the red line. So that deals with the effect of the cooling of the room. So that goes up to 32. So the proper temperature rise is not up to 29, but up to 32, and not 14, but 17. So what we do then is, then it says, work out the moles of sodium hydroxide. And what I'm doing here is I am trying to show what I try and do with my students. Because with students, what they find is when they see a question like this, they find it too much information. And they think, I can't do all that. So I try to get them to chop it down into smaller pieces. I don't mean with a pair of scissors. I mean to cover up some of the paper. So I say, okay, you're going to find the moles of sodium hydroxide. So in your mind, don't look at anything other than this. So the mass of the beaker is 8. The mass of the beaker and water, 108. So it's about 100 of distilled water. And oh, look. Beaker, distilled water, sodium hydroxide, 114. So now I just have to take the 108 from the 114, so 6.2. So if I can get the students to focus on just one small part of the question, they, like Iestyn was saying, one step at a time. In the UK, where we don't eat elephants, we have a saying, and it is about major tasks. The saying is, the best way to eat an elephant is one mouthful at a time. Because to try and put a whole elephant in your mouth would be difficult. Well, it's the same with this. We want to break the question down, focus on only one little bit at a time. The next bit was moles. And so the moles is grams over RAM, easy. For those of you who have come to some of my lessons with the students, you'll know moles are RAM underground is a good way of remembering. So it's 6.20 divided by 40, which is the the RMM of sodium hydroxide, which makes it 0.155. Then you need to focus on a different part of the question. Use your results to determine the molar enthalpy. Okay. So using your results, so first I have to work out the heat that has been transferred to the water to start with, not the molar enthalpy at all. So we call that Q. A lot of you will call that Q. So I say, okay, I've worked out the mass of water, 100.15 grams. I know that the heat absorbed, and they have to remember this, is the mass of water times the specific heat capacity times the temperature rise or drop corrected for cooling or warming. So it's 100.15 times 4.18, which is always given in the question. There it is. Times 17, which gives me 7 and a bit kilojoules. Then I want to turn it into the molar enthalpy, which is the energy change in this example divided by the moles in this example. So it's going to be 7.116 divided by 0.155, and there it is, 45.9 kilojoules per mole, which is probably about right. So let's go back over the question just for a minute, because what we're doing here is trying to break down the question into the parts which are important for the students. One, the plotting the graph is very simple. They have to make sure that it's a linear scale, obviously, so that each division is worth the same value. But once they've done that, and it's pretty easy to do it, it's the extrapolation. Here's the extrapolation. I normally take just the first few because that looks like a straight line. There we are. And the temperature should have gone up to here, which is 32. Measure it carefully there. Then what we try and do is to break the question into small bits for them, work out the moles of NaOH. There's the mass, here's the moles. I should have said RMM there, sorry. Then the molar enthalpy, well, I need to work out the heat that has been absorbed by the water, which is simply the mass of water times the 4.18 times the temperature rise. If they ask about K, tell them about Kelvin, it's important. So we get that, and then we divide that by the number of moles, and there we are with our answer. Now, there are lots of those sort of questions, and they're not actually very difficult. They're just very confusing to a student who isn't very good. But don't let them think, oh, I can't do this question. I won't even bother plotting the graph. Because plotting the graph and extrapolating and working out the first few pieces will be very valuable to them too. Okay. Yes. I often do these. This is a very simple thing which is available on the internet. You'll be able to see this one when you get the PowerPoint. It's a group sort and other things like this. It's very simple, but it's quite useful for the learners. You can ask one person at a time to do it. So we start, okay, we're sorting endothermic and exothermic, and I go photosynthesis. Oh, I think that's, oh, yes. So I just run through this. So combustion, that's, oh no, that's exothermic. Do you see what I mean? Bond making, oh, bendomexo, making mexo, that's exothermic. A cold pack, well, that's taking in heat, so it's going to be cold there. A negative energy change, so delta H is negative, that's got to be exothermic. Presumably this is a delta H, so that's positive, so that's in endothermic. Products lower than reactants. Products lower than reactants. Oh, that's got to be exothermic. Do you see how it works? The idea is just that the students can come and have a go at this. They can have a go on their own. Because I'm talking and doing this, I will probably get it wrong, which will be funny. Respiration, positive energy change, bond breaking. And then they can submit their answers, and you can do this as a class, or you can have little competition between teams in the class. Oh, thank God. Teacher Mark knows a bit of chemistry. That's good. Okay. So I want to get rid of that. Okay, so it's just a way of just at the end of a topic, just checking their understanding, which I think is very useful. At the end of this particular one, there's the knowledge check, and then at the end of this one, there's some other useful links, energy questions, some energy answers, and there's a teacher's site which you may well know, which is Form 1 to 4 Simplified Chem, which is really not bad. So you might find that quite useful. Okay. So that's really the end of enthalpy, energy, and so on. I hope it was useful. If you would like, I could do some of the questions, do some more questions of that last type, the one which is most confusing to students. If you want, I could do some more and submit the answers, the questions and the answers, okay? Okay, so we're going to move on, and we're going to start some organic. Where's organic? Whoops, where's organic? Ah, here's organic. Okay. In a minute, well, at some point, we're going to be doing a little quiz. Okay, we're going to be doing a little test. I'm not really going to test you because that's a bit unfair, really. But that's the sort of thing we're going to do. So, what I've got here is I've got a slideshow which I'm going to just tell you what I think is most important in organic chemistry. A lot of people don't like organic chemistry because it's got many individual reactions and bits and pieces which are quite difficult. I'm not going to look at organic chemistry in Form 3 yet. I'm going to look straight at Form 4. And if you look at it, the specification, the syllabus is huge. And it's got a really large amount of stuff on the alkanols, the alkanoic acids, the esters, and then silly things like detergents and soaps and polymers and why we add sulfur to rubber to make it into tires and so on. And some of the questions are really quite weird, but I am trying to focus this on the questions rather than just what it says there. Now, to my mind, what is most important from your students is to get them to do these things. Firstly, to be able to draw out molecules really easily. That's really important. Being able to recognize functional groups and homologous series, in other words, families of them, but being able to recognize them without any question. So in that case, what I often do is to show them lots. I draw lots on the board and I say, which ones are alkanols, which ones are alkenes, and so on. Being able to name molecules is very important. We'll be doing some of that. Isomerism, understanding its definition, but also being able to recognize it and recognize it when it's not. And then what I call the organic map. And I think the organic map is really vital. And then there's all the stuff like polymers and detergents. So I'm just going to run through my highlighters, which I tell the students they've got to be able to do. Firstly, in drawing out molecules, something that they forget is counting. They often mess up the counting. So alkanoic acids, they think, oh, well, it's 3 carbons. So they go CH3, CH2, CH2, and then COOH. Oh, hang on. No, that's butanoic acid. This 4 bonds off each carbon, 2 off oxygen, 1 off hydrogen, every one of them. I was doing some work with some of the centers and almost all of them, when they drew them out, missed off a bond or 2. So there were quite a lot of carbons with only 2 bonds or 1 bond, or there were hydrogens with 2 bonds. You know, a bridging hydrogen doesn't exist unless you work at Harvard. And when you draw out OH, don't draw OH as joined together, draw them out as line O, line H. It's really important. Naming molecules. I'm going to show you what I do just now on the other board, but I tend to go for different shapes around the different parts of the molecule. So we get something where we go, oh, it's like that. Sorry about the lines on this. I had to do them freehand with the computer, which was very rubbish. So I get them to do this, and I'm going to just show you how I do it, just because it's something which I think is worth passing on, because a lot of people, a lot of the teachers who I've worked with have said they think this is quite useful. So what I do is this: I pick an example of a molecule. So let's have. So I'll just make it up. So here it is. I don't know. Can you see that okay? Oh, it's a bit bright. Hang on. Is that a bit better? I hope that's a little. Can you see that okay? Just about? I hope so. So what I ask them to do is I get them to draw a circle round the functional group. Okay? So I draw a circle round the functional group. And I know that that is the end of the name. Okay, so I've recognized that this is an alkanoic acid, so it's going to end in anoic acid. So I teach the students what the ending of various functional groups are. That's really quite important. Sorry, I just need to close the curtain. It should be a little bit easier to see, perhaps. And then what I do is I draw a rectangle round all of the carbon chain, so I can work out what the root, the skeleton is. So this helps me not get alkanoic acids wrong, because a lot of the time students will forget that that carbon is part of the name, is part of the whole molecule. So they might have called this 1,2,3 propanoic acid, and it's not, it's butanoic. So 4, so it's butanoic acid. We don't need a number because it uses 3 bonds. Obviously, it's at the end of the chain. At this point, I also number the chain starting at the functional group. 1, 2, 3, 4. And then I use a triangle around any substituents. So I've got 2 substituents here. They're both chlorine, so it's going to be chloro. But there are 2 of them, so it's dichloro. And they are on chain positions 1, 2, and 3. So it's 2,3 dichlorobutanoic acid. Now that's a pretty complicated molecule, and most of your students wouldn't have a chance with that. But this is a point where you can do some differentiation. Put up some molecules, some easier, some more complicated. So the very good students can have a go at something more complicated, and the less good students can still feel that they're learning because they're still able to name something. So circle round the functional group, box round the main chain, substituents triangle, and that mentally keeps it all separate. The problem comes when you have something drawn like this. When we talk about isomers, a lot of students think that just by bending the molecule, we get an isomer. So I get so they say, let's draw all the isomers of C5H12. So they go 1, 2, 3, 4, 5. That's one. Good. Don't worry about the hydrogens for the moment. Then they go 1, 2, 3, 4, 5. No. So what I try and do is I say, imagine that this is a string of beads. Pull it straight. Are they the same? Or name them. Because this is going to be, it's no functional group, so it's an alkane. So it's going to be ane. It's 5 carbons, so it's pentane. This one here, that is the longest continuous carbon chain. That's pentane. It's the same molecule. Okay? So when they bend molecules, just tell them, imagine grabbing hold of both ends of the molecule and pulling it, and they will soon see that it's whether it's the same. Okay. Where's he gone? Oh, there he is. Okay, so circle around the functional group. If I were you, I would give them a table, make a table of the functional groups and the name endings, the length of the skeleton, metheth, propute, and so on, and then the names of the substituents, and they'll be able to do it really easily. Okay, I'm sure. Sorry, that's my wife just going past. Now she's she's much cleverer than me. She's got a PhD in biochemistry, so she is doctor, and I have to go, yes, I will do the cooking of the ugali tonight. Right, share my screen. Mr. Snell, you are stupid. Yes, I know. So here we are. So sorry, it's just, what's happening here? So there's the naming. Isomerism, I've just said, they need to know the definition. Simply bending the chain doesn't make a new isomer. And then teach them about geometric isomerism and double bonds and the same side and different sides and so on. But the most important one is the organic map. And in KCSE, there are a lot of questions like this, which are really quite hard for the students. Obviously, you guys are going to go, ha, it's so easy. And I'll just give you a moment to look at this and just see if there are any problems where you think, hang on, I'm not completely sure about that. Do the first 2 bits of the think and pair and share. Just have a look at this question for a moment. We're only going to spend a few moments looking at this, and then we're going to take a bit of a break. But just think about it on your own for a moment, and then share your ideas with somebody else near you, and see if you can get to an idea, get to more ideas between you. Okay, have a look. So there are some, we're trying to identify the steps, obviously. What petroleum to ethene, what step is that? Oh, God. What's step 8? Ethene to polythene. Oh. Step 10. Ethanol, ethanoic acid. Oh, God. So there would be questions like, what is necessary for step 10? What might you see in step 5 if you used, well, firstly, what would you use and what might you see in a color change and so on? So we'll just have a few moments looking at that before I show you the map. Just have a look, just have a chat with somebody else. Some of it's quite hard. Just count up for yourself, see how many of the 11 steps you would be able to do. There are 11 steps. How many of them would you be able to do? I know most of you won't have 11 fingers, so we'll take 10 as a maximum when I ask you how many you would have got. Don't worry, it's not a test. It's not a test. If you want to put up 10 fingers anyway, I don't care. Make it a little bit bigger and go around. Ooh. Well, it's quite, some of it is quite interesting. Okay. Okay. How did you get on? How many do you think you'd be able to do? Do you think you'd be able to do all of them? If you think you can do, or if you thought, yeah, I can do that. Seriously, organic chemistry is one of those areas which you either, I love it, or I really don't. And sometimes it's like, ooh. So how was it? Was it okay? Is that okay for everybody? Can you do all those? Or can you do most of them? Or you can do, oh no. Oh, you can all do all of them. Ah, well. Mathari say they can all do all of them. They come back first from lunch. So they get gold medal there. How about Kibera? Kibera, how are you feeling about organic chemistry? Oh, they're champions as well. Okay. Kisumu, organic chemistry, okay? Okay, and not quite so okay. Okay, right. My idea for teaching organic chemistry, we'll stop for a 10-minute break in about 5 minutes. My idea is that you need to get them to learn what I call the organic map. I'm going to show you it now, and I'm going to explain why. Organic chemistry feels like many small reactions, feels like many individual reactions. But if you can remember the map, which I'm going to show you, they will get an overview, a sudden understanding. It's like doing a jigsaw. If you have ever done a jigsaw, you will know what I'm talking about. If you do it without the picture and you are trying to just put the pieces together, and then suddenly you go, ah, it's a lion eating an antelope. Okay. Yeah, that's what organic chemistry is like. Let's have a look at the map. Excuse me. So there's the question. Here it is. Here's the map. Now I'm going to show you the whole of the map. I'm going to show you how I construct it. So I start with glucose. I make an alkanol. I make an alkanoic acid. They make an ester. That makes an alkene, but an alkene can make an alkanol, alkane, polymer, soap. Now, if the students can have a view, a mental memory of this map, and they can start to test themselves on how you make an alkanol from an alkene, steam, 300 degrees, 70 atmospheres, phosphoric acid catalyst. Now that on its own is a horrible piece of information to remember. But if they can remember that alkenes can be turned into alkanols by adding water, they are on their way. If they can remember that potassium dichromate or permanganate and acid will make an alkanoic acid, that's fantastic. And then there are the types of reaction: oxidation, reduction, hydration, dehydration, saponification, and so on. And you can get them to do it so that they just number these, and then they can test themselves, or they can test each other. Those little revision cards that Yestin talked about, they can make these, and they can do these, which are great. Oh, yes. Oh, it's called hydration. I remember. Oh, yes. Okay. So then we need to know about how we test for different chemicals. That's easy. Testing is pretty easy. And then we're going to do some problems about how you make this into that. Okay. So we're going to go back to the beginning of this. Stop at that. I'm going to stop sharing now. We're going to take 10 minutes now. So if you want to just go and get away from here for just 10 minutes, I will be starting again in 10 minutes, not 11 minutes, Kasumu. Mathari, not 9, okay? Oh, Mathari, we like 9. Okay, so take 10 minutes, get up, walk around. Please get up, walk around, talk to somebody, discuss whether you think there's a question which you want answered, because I will be asking if there are questions you want answered. Have a walk. I'll be back very shortly. Okay, we're going to move on. I'm recording this so that if Kasumu can't get back, they can see it later, maybe. So we're going to get on with it. I hope everybody's back who wants to be back. I guess some people have probably run out the back, going, I never want to do any more chemistry. That's okay. I'm going to show you the organic map. I'm going to talk about the map. I'm going to write some equations. I'm going to get you to write some equations. Then we're going to have a small quiz, which you don't have to do. It's not a test. I wouldn't test you. You're chemistry teachers, not students. But I want to show you what I do with my students so that you can get an idea of what might be useful to you. I'm quite sure that the vast majority of you don't need these sessions, but if a few little pieces of information have helped, that's great. If they haven't, then you can come and teach me, and that would be fine. But I'm just trying to show you some of the things which I do, and most of my students have done pretty well. So here we are. Come on. Okay, the map. So it's up to you whether you construct one like this. It doesn't matter, does it? It doesn't matter the order of it. It doesn't matter where the individual things go. I just think in terms of from left to right. I think simple chemicals like alkanes and alkenes on to more and more complicated and more oxidized chemicals on the right-hand side makes sense to me. There are a whole bunch of conditions and so on, reagents and conditions. I color them differently. So I put the reagents, the reactants in one color and the conditions in a different one. So for instance, in alkene to alkanol, water is what is actually going to do the change, but the conditions are 300 C, 70 atmospheres, H3PO4 catalyst. Going backwards, the thing which is going to do the damage is concentrated sulfuric acid, but it has to be at 170 degrees or so. Now, you probably know that there is a way of making alkenes to alkanols using concentrated sulfuric acid, but at 70, followed by water. So I'm not going to look at this. What I'm going to look at is the equations, and just so that everybody is completely confident with those, because there are some which are more important than others. So here I am. I'm just going to go to my other board and write a couple of equations, simple equations. I hope they're useful. There are some confusions about some areas. So for instance, when an alkene reacts with bromine water, it is very tempting to write the product is going to be 1,2-dibromoethane, and it's not. Your student will probably get the mark if they write 1,2-dibromoethane, because there is some formed. One, 2-dibromoethane, but actually, and you may know this, it forms 2-bromoethanol. 2-bromoethanol. Why is it 2-bromoethanol? Remember the naming. Circle the functional group. Rectangle, the longest chain. Triangle, the substituent. The end of the name, ol, anol. Ethanol. 1, 2, 2-bromo, ethanol. Okay? So that's actually what happens, but you can't write an equation for that. You can only say this is the product. You can't write an equation from Br2AQ to this because there's no OH in this. You would have to write it with BrOH, which is in bromine water. So let's look at the most common ones which they ask to have equations written. So let's look at the oxidation of an alkanol ethanol. We don't normally write K2Cr2O7 or KMnO4. We just write O in square brackets for an oxidizing agent. What goes wrong then is that the students tend to get the numbers wrong, the numbers of oxygens which are going to go on. We could write it with Cr2O72- H+ and so on. We could do that, but there's no need at this level. If you were going to be teaching in a university, and some of you may, you will have to write it with Cr2O72-. So this is going to go to CH3COOH ethanoic acid. What the students have got to do then is make sure that they have counted up properly. Because when I teach students much lower, like 14-year-olds, to balance equations, I get them to write down underneath the arrow the number of each element in the equation so that they can get it right. So I go carbon, hydrogen, oxygen, 2 carbons, 2 carbons, 6 hydrogens, 3, 4. And then automatically I go, I must have produced something else, and there's something else. If it's an oxidation, will be water. So now I've got 6. But look at my oxygens. At the moment, I've got 1 here, that's 2, and 3 there. And this is where, hello, show it up again. I'll have a look. I'll look at all of them. What name is given to the type of reaction in step 7? Okay, I'll have a look. I'll have a look. So this one here needs that. And many of the students I have taught in Nairobi have forgotten this. And then remembering everything else is rubbish. You've got it all wrong. Without this, it's not a correct equation. So train your students to do something like this so that they don't misbalance a simple equation. Okay. In a dehydration, all they write is the original chemical turns into the product, ethene in this case, and water. We don't have to do anything else clever. In the same way, in the opposite direction, for the hydration of ethene, we just write C2H4 plus H2O goes to C2H5OH. Simple stuff, okay? So, but just try to make sure that they can do oxidation with O in square brackets and hydration, dehydration. Okay, we're going back to the questions. And the person who's disappeared, me. Okay, share the screen. Okay, let's, come on, get off. Right, let's go back to that question because I should probably have gone through all of it. Let's look at it. Whoops, hello. Okay, here we go. Step 1, to produce ethene, that's obviously cracking. They should know that the temperature is about 700 degrees and the catalyst is normally aluminium oxide, but could be other oxides and so on. So that would be step 1. Step 2 is up here. Step 2, ethene to ethane, that's a hydrogenation. So it's hydrogen, and that will be a nickel catalyst. And it's normally just a bit over room temperature, like 70 degrees. So nickel and hydrogen for that step there. Step 3, where on earth is step 3? I can't find step 3. Well, we'll go for step 4. Here's step 4, glucose to ethanol, that's obviously. And if it's going to be to ethanol, we should say that it's going to be fermentation, and that will be at around about 37 degrees with yeast and no oxygen. That's really important. And then it will have to be fractional distillation if we're going to end up with ethanol. Quite often these questions have, how do I turn glucose into impure ethanol and then impure ethanol into ethanol, into pure ethanol? And that would be the fermentation followed by the fractional distillation. Oh, there's step 3. My apologies, I couldn't see step 3. Ethene to ethanol, that's just hydration, that's water, and 300 degrees Celsius. Students can quite often remember the numbers, which are 370, but they have to remember that the 300 is the degrees Celsius and the 70 is atmospheres and phosphoric acid. Step 4 we've done. Step 5 is esterification. Step 5 is ethanol to ethanoic acid. That's oxidation, which is K2Cr2O7 and dilute sulfuric acid. And we would normally heat it under reflux so it can't disappear. That's quite an important detail, really. Sorry, just got to move something. Okay, Step 5. Step 6 is up here. Ethane excess. Whenever they say excess oxygen, they mean simply combustion. So they quite often, here's another one down here. There's step 6 and step 9. They're both just burning. Okay, ethane, ethene both burn to give carbon dioxide and water, as does ethanol, as do all of them actually. So that's step 6. Step 7, aqueous bromine ethene will produce, that's the one which I was just writing. Product R is 2-bromoethanol. 2-bromoethanol. If you write 1,2-dibromoethane, you are also correct. Both of them are produced, but the more prevalent product is bromoethanol, 2-bromoethanol. Okay. Step 8, ethene to polyethylene. That's obviously polymerization, and it's normally fairly high pressure and an initiator or catalyst and some heat. Step 9, ethanol, that's burning. Step 10 is ethanol and ethanoic acid. That's esterification. And for that, we need some warmth, but we also need a concentrated sulfuric acid catalyst. It's only a few drops, but it is a concentrated sulfuric acid catalyst. Step 11, ethanoic acid to calcium ethanoate and carbon dioxide. Well, if we want carbon dioxide, it will be a carbonate, because ethanoic acid is a weak acid, but strong enough to liberate carbon dioxide from a carbonate. So that would have been calcium carbonate. And calcium carbonate and ethanoic acid will form calcium ethanoate and H2O and CO2. Okay. So that's all the bits and pieces there. Has anybody got any problems with any of those? Are those okay? Or has anybody got any questions with that particular question, that one there? No, are we okay? Okay, I'll move on. Okay. So here's the map, which I think is useful. I do it with reagents and conditions, and then types of reaction, like this. You'll get this when you get the PowerPoint. Get students to write it out with numbers and test them. What's at number 1? What's at number 2? What's at number 5? Okay, who's got the answer to number 8, and so on? Okay, that's all okay. Testing, they should know the tests, obviously. Bromine, water, and burning for the alkanes, alkenes, alkanols, and alkanoic acids. 3 tests, really. I don't know why. Oh, I think it's dropped off the bottom. Burning, yes, because alkanoic acids don't burn as well as alkanols. Oxidizing agent, obviously the alkanols can be oxidized and the alkanoic acids can't. And adding sodium carbonate, because the alkanoic acids will liberate carbon dioxide and alcohols won't. Esters, the only test that you have in KCSE is a pleasant smell, which they do have. Then I would normally give my students a group of chemicals. How would you turn this into that? And let's take this example here, the glucose into ethene. That's not a one-step process. So they would have to say, oh, glucose, yes, I can't make it into ethene. I can turn glucose, I can turn it into ethanol, I can turn ethanol into ethene. So sometimes multi-step reactions are very useful. Palm oil to soap, that is saponification. Palm oil, any oil or fat with sodium hydroxide will make soap, and so on. Okay, there's that one. Why is it not moving? Oh, I'm sorry, I've lost the slide. Oh, well. Okay. The only other 2 parts of it we will see in just a minute in my little quiz. So we're going to have a little we're going to have a go at some questions which the students have to do. You could have a go yourselves, see how many you get. It's not really a competition. It's just that this is the sort of thing I quite often use with the class. I quite often say, okay, we're going to do a little quizette, I say quiz, and then I put the word "et" on the end, which makes it less serious. So I say, because a lot of students get scared by exam. So I say, this is not exam. It's not even a test. It's not even a quiz. It's a quizette. And that way they get less scared, which is stupid, but it works. I regularly do this and get them into groups of 3 or 4, because then the timid ones, the frightened ones, will be helped by the more confident ones, and so on. We're just going to have a look at the answers. Look at the questions, the answers. I will do it though as a little quiz, so I'll show you how it works. You will get a copy of this. So here we are. So I do a lot of these. You can do them spoken, you can write them on the board, you can do them like this, it doesn't matter. So question 1, what is the molecule CH3CH2? And this is to get them used to identifying the functional groups. If anybody has a problem with this sort of thing, get them to draw out the molecule, remembering the rule about the number of bonds from carbon and so on. And I expect that you're all laughing and going, oh, I know what that is. It's there. I do these as multiple choice because then it narrows their possibilities, and you know that this one is D or propene. That's great. Okay, so there it is, propene. There has to be a double bond between these two. All right. Now, the students then feel, well, I often then say, who's got 100%? Okay, should we stop there? No, okay, here's another one. What's this molecule? CH3, CCCH3. Now, that needs people to realize, to count up the number of bonds and to think, well, what must be happening between these central carbons? Here are their options. And that there between the carbons, if we actually drew them out, the CH3 is only attached to this carbon by 1, that by 1. So between these two, there must be 3 carbons, and therefore the answer is -ine. It's an alkyne. Okay, it's good to have an explanation which shows that there is a triple bond here, so it's an alkyne. Question 3. What's this one? Here's your options. And of course, it's propan-1-ol. Propan-1-ol because the OH is on the end. A. Got 3 carbons, prop, OH makes it an alkanol, and it's on the end. Easy. Easy. What about question 4? Oh, this is where they start getting unstuck, the students, because they count the 2 carbons. They sometimes have recognized COOH, but they've counted 2 carbons. Here's the options, and this should help them. I've done this to help them, to make it all prop. But most of the students which I have come across in Kenya have thought it was propan-1-ol. Most of them have thought it was propan-1-ol. It's not, obviously. COOH, alkanoic. COOH, alkanoic. Easy, just get it drummed into their heads, get them to recognize. It's one of those key skills that they have to be able to do. Okay. And then I ask them how they're getting on. Now, the reason for that, at the beginning, I said it's important to feed back regularly to students. They need to know how they're getting on. If they're doing it in a group, they will feel less threatened because they're in a group, but they will also, underneath it all, they will know that they didn't know the answer to number 2, 3, and 4 or something like that. And they will know then that they have to do that 10-minute thing that Yestin was talking about. It's really important to allow students to know how they're getting on. Really, really important. Do you want to do some more? Should we do some more? Let's. Who's got 4 out of 4? I have. I got 4 out of 4. Have you got 4 out of 4? Have you got 4 out of 4? Mathari, have you got 4 out of 4? Yeah, that's a lovely shirt. I love that shirt. Kasumu, have you got 4 out of 4? Kibera have, yeah, Kibera. Too confident. Okay, I'll make it more difficult. I'll make it more difficult. Always make it more difficult. Okay. So next question, question 5. Wow. What do we got? What could be oxidized to form CH3, CH2, COH? Okay, here's a question for you guys. What would be oxidized? Sorry, what would be the oxidation product of C? What would be the oxidation product of C? Any idea? Anybody remember their chemistry? Propan-2-ol oxidation. What would it make? Propan-2-ol. This is beyond form 4. No. What would that's the correct answer to the question. What would propan-2-ol be oxidized to? If it was oxidized, propan-2-ol would be oxidized to what? Anybody know? Anybody know? It's propanone, acetone. It's called propanone or acetone. Okay, let's go on. So that's A. That's the right answer for everybody. Next one. What chemicals could be used to oxidize an alkanol? What chemicals could I use to oxidize an alkanol? Here are your choices. Here are your choices. And the answers are A or D, because A was K2Cr2O7 and D was KMnO4. So orange potassium dichromate, purple potassium manganate, turning green and colorless. Important that they know the color changes. Question 7. I've got some water and I want to make an alkanol. What could I start with? I have some water and I want to make an alkanol. What could I start with? In other words, add water to which one of these and will I make an alkanol? Now, if you just added water to any one of these, nothing will happen. But we are going to assume that you are allowed a catalyst, a bit of heat, pressure, those sort of things. So what should I start with? Hang on, hang on. Show me an answer. I can't see. A bit closer, please. Yes. The answer is C. Obviously, it's C. Oh, yeah, I knew that. It's so easy. Alkenes can be hydrated. We would need the conditions, which are the H3PO4, 300 degrees, 70 atmospheres. So here's number 8. Write an equation for the hydration of ethene. Write an equation for the hydration of ethene. And here's the answer. C2H4 plus H2O goes to C2H5OH. It's simple addition, nice and easy. C2H4, H2O, C2H5OH. Easy, Kubera, huh? Too easy? Yeah, okay. Here's question 9. Here's that equation of ethanol to ethanoic acid. We've just done it. C2H5OH plus O in square brackets goes to hopefully you can do it and not worry about it. I wish I could see you, Kisumu. I'm quite sure you're right. Do you want to run up to the camera? I'm quite sure you got it right. You're teachers, man. Here we are. Here's the answer. Yeah, 2 oxygens because we've got 3 oxygens in the product and only 1 in the reactant. C2H5OH plus 2 O in square brackets, CH3COOH and H2O. Okay, we're nearly at the end, in which case we're going to be doing some other things. I want to make an addition polymer. What could I start with? I want to make an addition polymer. What could I start with? What could I start with? I'm sure you know. And the answer is yes. Yeah. Yes. The answer is C, because alkenes. Oh, sorry, I missed you, Kasuma. Oh, Kasuma, come back another time. Right. I think there's just a couple more. If you were on, and this is really powerful for the students because they need to know you don't have to get 100% to do brilliant. You don't even need 70%. If you could get 50%, you'd be going really well. If you got somewhere between a third and a half, you would still be passing, and so on, okay? So it's really important to give them, the people who are not very confident, the idea that they can do them. Here's a polymer. I'm only going to give you like 1 minute to look at that. What's the monomer? Identify the repeating unit. It's gonna be A, because there are 3 carbons in the unit. Okay, there. Identify the repeating unit. Kisumu is keen and good. Well done. Here comes question 12. What is needed for the hydration of ethene to form ethanol? That's the thing which I just dealt with, so I'm not even going to spend time doing it. 300 degrees, 70 atmospheres, phosphoric acid catalyst. These seem like stupid things they have to know, but they do need to know it. Only 2 more questions. Right. If you start with propene, and the RMM of the polymer is 525,000. How do we work out how many propenes made it? Okay, don't worry about actually trying the calculation. It's important that they know how to do this. So it's the RMM of the polymer over the RMM of the monomer. So it'd be, because propene weighs 42, it's 525,000 divided by 42, which is 12,500. It's a simple calculation, but they need to do it. What homologous series does that belong to? My students learn that COOC is a misspelling of cook. And they know that the pleasant smelling esters are used to flavor foods. So they know every time they say COOC, that's an ester. Last question. Which one of these would be better with hard water? A, with that, or B, absolutely, thank you. And the answer is B, because that is a detergent, not a soap. Right. Okay. Okay. So that's really most of the end of organic for now. What I'm going to ask is whether you have any individual questions which you would like to ask. Any approaches to the subject, any parts of the technical side of it which you would like answering. My syllabus is very different from yours. So there's a guy at Silver Springs called Samuel, who almost every time he comes on a lesson, at the end I say, do you have any questions? And he says, yes. I want to go through a certain process. And the process is always the same one, because he just can't get it. So I'll see if anybody comes up with that question just now. It's one for producing sodium carbonate. The process starts with an S, but I'm not going to go through that. Does anybody have any areas of the syllabus that they would like to go through? And are there any areas of the syllabus that you would like me to go through in another session sometime, or to record and send to you, because I could do both? Okay, so either switch on your microphone or just write it on a piece of paper and hold it up. Are there any questions about Form 4 chemistry which you think you would like a hand with? Have a chat with your neighbor, just see if there's anything that you would like doing now, because we have, I think, about 15 minutes left. Does anybody know what that process is for making sodium carbonate? It's a horrible one to teach people. It really is. Guy with the stripy shirt in Kisumu who's walked off to kill himself because he had enough chemistry for the day. Any topics which anybody would like to go through in a future session or now? Ooh. Any questions that somebody would like to? Ooh. Solubility, acids and salts. Okay, from Mathari we have, I'm just going to write this down. Metals, yeah. So Mathari would like solubility, acids and salts, and metals. What would other teams like? Oh, or the mole concept. I did the mole concept, I think, in the first session, which I did for teachers, I think. But yeah, we could do moles. Kisumu and Kibera both know everything. It's only Mathari who don't know anything, which is good. So Kisumu, they got it all sorted. So would other centers also like, I've got 4 here. I'd like it to narrow it down to 3, but I could do a bit of solubility now. If nobody wants, I could do a little bit of solubility. Oh, good heavens. Okay. The mass of the molecule, hydrogen, no. Hang on, let me take a picture of that so I can leave it there just for a minute. Hang on. Okay, you can put it down. I've got a picture, I think, of it. I'll just check. Okay, that question there. The question here, guys. Oh, industrial. Contact and Ostwald, yeah? Contact. Well, Contact and Ostwald, we would do if we did sulfur and nitrogen. Kibera, what you have to do to start with is just to go, okay, if one molecule weighs 9.33 times 10 to the minus 22, I have to find what 1 mole will weigh. We know that it is a hydrocarbon. So what I have to do, oops, they've disappeared. Oh, okay. Okay, I'm going to do 5 minutes on solubility because that came up and it's really quite simple. Okay, so I'm going to go to the other camera and I'm going to just do a little bit on solubility. So here we go. Okay, solubility, very brief look at solubility. The first thing to know is that the solubility is measured in grams of the solute per 100 grams of water. It's always the same. And it is always plotted against temperature. Now, sorry, can you see that okay? Just about, okay. So for solids, the line may be fairly low, but in general, for solids, it goes up. In general, some go down, but most of them go up. If I want to find the temperature at which a certain mass dissolves, all I have to do is to draw that to here and down and read it off. So in other words, if they said, okay, I want to know at what temperature 40 grams will dissolve in 100 of water, then I just find 40 up here, go across and down. But a much more common question is how much would be precipitated out if I cool it down. So if I cool down a particular temperature, let's put some numbers here. Let's make this 100, 50, and 0 down here. And let's say that's 90, and I'm going to cool it down to 70. So what I do is I go, okay, at 90, that is the solubility of this solid. At 70, at 70, this is the solubility. So if I had a test tube and it had this solution in at 90, and I allow it to cool down to 70, 20 degrees, the amount of solid dissolved in there will drop from 100 down to 50. So 50 will come out of solution, and I will see it going cloudy. I will see crystals forming. I will see the precipitate. This is used to separate different solids because often they will talk about two solids which have very different curves. So it's called fractional crystallization. And it goes like this. Whoops. Let's say I have potassium nitrate and potassium carbonate. Potassium nitrate is really, really soluble and dissolves much better in hot than in cold water. If I have potassium nitrate and potassium carbonate mixed together, and I take it up at a particular temperature, then just by cooling it down from, let's say, 90 down to 50, I can get most of the potassium nitrate to come out of solution. But look, at 50, almost all of the potassium carbonate is dissolved. And therefore, it is not going to come out of solution. There's no difference between 90 and 50. So the nitrate will come out of solution. So I let it cool down and then I filter it. But the potassium carbonate stays in solution. That's what we call fractional crystallization. For gases, something else happens. In general, gases become less soluble. You may know that we are worried about climate change and rivers and their ability to support fish and so on. The reefs off Kenya and so on are going to be much, much damaged by warmer water, because this is what happens to the solubility of a gas like oxygen. And because this happens, as water warms up, it can carry less oxygen, so the fish die. That's the trouble. Okay? Okay. Oh, Kisumi's Kibera. Ah, Kibera, right. Where's your man gone who had the question? Have we got any more topics? I'm going to tell you the topics which we have at the moment, and then you can tell me yes, no to the different ones. We have sulfur chemistry and nitrogen chemistry, which will include the contact process and the Ostwald process. Would people like to have sessions on sulfur and nitrogen? Sulfur and nitrogen, yes or no? Kibera? Some yes, yes. Okay. Kisumu, yes or no? Okay. I know that Matari wanted that. Moles. Who feels that they need help with moles? The mole concept and mole calculations and so on. Need help? Don't need help. Would like some help? Kisumu say yes. Kibera? More people? People at the back? People at the front always get the say. Okay. Acids and salts, do we want help with that? No, yes, no. Acids and salts, are they okay, Kisumu? No, are they okay or not? You don't need help, or they're not okay. Sorry, I asked two questions there, didn't I? Do you want help with acids, or do you not want help with acids? Not, okay. What about metals? Kasumu, metals, help, no help needed. Kibera would like, Kasumu, no. Okay, so it looks like sulfur, nitrogen, and moles. We could do sulfur, nitrogen, and moles. That would be okay. We could do that quite easily. Ah, Mathari's back. Okay, cool. Okay, guys, that is just about it. We're about finished. Like I said at the beginning, it is very difficult because you will be at various stages. Some of you will be relatively inexperienced teachers. Some will be really knowledgeable, very experienced. I'm sorry if I made it too easy or too hard, whatever, but I hope some of it was useful. I'm going to stop recording now.